Welcome to Chemistry with Caroline. In this video, we're going to look at Lewis acids and bases, and this is the broadest definition of an acid and a base, and much broader than what we think of when we think back to our Gen Chem knowledge. So let's just break down how we think about an acid and a base with Lewis terminology. And in this case, we're not even thinking about protons, we're just thinking about electrons and what electrons do. So an acid is an electron acceptor. Okay, and a base then is going to be an electron donor. And these definitions are complementary to what we already know. We've thought of a acid as a proton donor, right? So if it gives up an H with no electrons, it's got to accept those electrons, right? A proton is a positively charged hydrogen. And a base is an electron donor, and it's a proton acceptor, right? And it uses those electrons to accept the proton. So these are complementary, but we don't even actually need a proton for a Lewis acid-base reaction because we're only talking about what the electrons are doing. So let's go to the next page and we'll look at an acid-base reaction and observe what's going on. Okay, so here I'm going to use, again, just a generic acid-base reaction. So I'm going to use HX as my acid, and I'm going to use B as my base. I'm going to put a lone pair on it and make it negative, okay? So this is my acid. This is my base. These are in equilibrium with one another. So now if I draw my mechanism arrows to show what's going on here, the base is going to use its electrons. It's going to donate its electrons to accept the proton. And then the acid is going to donate the proton and accept those electrons, right? So a acid is an electron acceptor. And we can see that happening in that second arrow there. And also a proton donor, right? If I think back to like a Bronsted-Lowry definition. A base is an electron donor, and we can see it doing that with its lone pair of electrons. And then it is a proton acceptor as defined by Bronsted-Lowry. So again, here we're really thinking about this in terms of the electrons and what they're doing, but they are complementary definitions. It's just that one considers electrons and the other considers where the proton is going. So again, that would give me my conjugate base, right? There's my conjugate base, that's X minus. It accepted electrons and donated a proton. And then my base is now protonated. It's neutral. So that would be my conjugate acid. It donated electrons and accepted a proton. So now let's look at an example where there is not a proton transferred, but by Lewis acid-base chemistry definitions, this would still be a acid-base reaction. Okay, so in this case, I'm drawing the lone pair on my nitrogen. Nitrogen is neutral when it has 3 bonds and 1 lone pair of electrons. Aluminum might not be a compound that you're quite as familiar with. It's a metal, but it's kind of right on the metal-non-metal line. And aluminum is trivalent. It makes 3 bonds. I'm going to use these wedges and dashes. A wedge means that something's sticking out, and a dash means it's going back. I just want to draw what this looks like for you so you can understand why this reaction is going to happen. The aluminum has 3 bonds, and then it has an empty p orbital, okay? So that makes it a good electron acceptor. So if we think about our arrows here, what's actually happening is the aluminum doesn't have any electrons on it, okay? And the chlorines have full octets. They're bonded to the aluminum, and they've got their lone pairs. And so this nitrogen is going to donate its electrons to the aluminum, and it's going to make something called a Lewis acid-base complex, okay? So they're going to be kind of stuck together. So the aluminum is still going to have the 3 chlorines on it. And now it's also going to have the nitrogen on it. Okay. Now the aluminum was neutral and it just accepted electrons. Electrons are negative, so the aluminum's now negative when they're stuck together like that. The nitrogen was neutral and it donated electrons. It lost electrons, so it's going to be positive. Okay. So if we think about this, the aluminum was the electron acceptor, so it's going to be the Lewis acid. Right? It's the electron acceptor. And then the nitrogen is the electron donor, so it's going to be the Lewis base. Okay, and this is a Lewis acid base complex. And I mean, as you can see, you have two neutral molecules to start with, and then this thing that's charged, right, that you end up with. These are commonly intermediates in reactions. So as organic chemists, we often put in a Lewis acid to activate something to make it more reactive so the reaction can go. So it's important that you understand what a Lewis acid and a Lewis base are and how they can react with one another, because it's going to come up as we start talking about chemical reactions. All right, so I'm going to leave you with some common Lewis acids. Those are the species that are generally more difficult for students to identify. A Lewis base is going to have a lone pair on it, right? But a Lewis acid is going to be able to accept electrons, and that can sometimes be harder to identify. So a couple of common ones are in group 3. In the last example, we looked at aluminum. Directly above aluminum is boron. And both of those elements are trivalent, and they have an empty p orbital, so that makes them good Lewis acids. They're good electron acceptors, and we'll see that commonly as we go forward in OChem and we do some organic synthesis. And then the other type of element that you'll see doing this is the transition metals. So transition metals really have a kind of entirely different type of chemistry, and in organic chemistry we use them often as catalysts for reactions. The common transition metal that you'll see acting as a Lewis acid is iron. And typically that's going to be an iron with 3 halogens on it for organic chemistry, so like FeCl3 or FeBr3. So if you can kind of just remember that boron, aluminum, and iron are common Lewis acids, that can help you get comfortable with the concept. And then from there, as you have more experience, you'll be able to identify them more easily. So this has been a look at Lewis acids and Lewis bases. If you found this video helpful, please like, subscribe, and share with your friends. Thanks.